only yes because I think there's people coming. In any case, I'm gonna start with the introduction, just welcoming Maria to our series of seminars. This is the first seminar of the year 2024, and well, thank you, Maria, for being here. As you know, we have initiated a series of seminars, internal seminars, people that has joined us recently, September. And this is the last of these 3 seminars, including Miguel Encinar and Gabriele de Sena. All right, so I was saying that Maria joined us in September. She was working in Universidad Rey Juan Carlos, where she got the PhD. And she's currently visiting professor in the aerospace department with us. Okay, she's mainly interested in stochastic optimal control and its application to a quite nice bio-inspired activity, which is the flight information, which has been explored in the last years by Airbus, Boeing, as an activity or a strategy to mitigate CO2 emissions. And she did a research stay in Delft University of Technology, and she has been also quite engaged in communication activities. She got a 3-minute thesis award of the Community of Madrid. In this contest, some of you have been working in the PhD. And she also got the Extraordinary Doctorate Award by Universidad Rey Juan Carlos in 2022, I believe. Thank you for being here. Floor is yours. I think it's a good opportunity for all of us to get to know what new people is doing, establish some contacts, and eventually cooperate and collaborate in research activities. So thank you, Maria. Floor is yours. Okay. Go ahead.
Thank you so much, Manuel. Sorry. Thank you, everyone, for coming here. Especially, I want to say thank you to the department and to the PhD program for giving me the opportunity to share my research and maybe looking for new collaborations, synergies, whatever. I'm going to start with a presentation. I'm going to present a new approach to the formation flight for commercial aircraft. Here it's the outline. Let's start with a brief introduction to the issue and the motivation to this work. So, as all of you know, we have a huge talent in the whole aviation sector that it's ensuring the sustainable future of aviation. And this involves 2 main issues. One, the environmental impact of aviation, but also we need to increase the capacity of the ATM system. Fortunately, formation flight can help to get these two to get these 2 issues. But when we talk about formation flight, what are we talking about? It's just when we have 2 or more aircraft flying at a short distance between them. We will talk more about this, of course, but just flying too close from each other, they are going to achieve some aerodynamical benefits. As with many other engineering ideas, this idea of formation flight to aircraft arose from the observation of the migration of the birds, like for instance the goose. It's very typical to see in our sky this kind of V formations. It has been demonstrated since the 70s that flying in this V formation gives the birds significant energy savings. And in the last 3-4 decades, this was extended to aircraft, demonstrated that they also can achieve these benefits. So the principle behind all of this is that any aircraft flying, it's going to induce some swirling motion to the air, and we are going to have two different regions, some upwards and some downwards fields, and a second aircraft flying in one of these upwards fields, like this or in this region, are going to increase its apparent angle of attack, and therefore it will reduce their induced drag. So this is going to imply quite a significant fuel reduction and, of course, a reduction in the emissions of this aircraft. We can have different classifications of deformation. One of the most common is based on the shape of the formation. We can have inlay formation or echelon formation, V formation, in which we only have one leader and the rest of the aircraft are going to be trailing, or the inverted V formation, in which we have two leaders. But a more interesting classification for this work is based on the longitudinal distance between the aircraft. Depending on this distance, we can have a first classification, close formations, in which the aircraft are flying very close from each other, typically at maximum distance of 10 wingspans. Of course, these kind of formation are going to give us the greatest benefits from the formation. However, we are going to focus this work in standard formation because they are safer. We are flying at a greater distance, so as we know, safety is a key point for aviation. So we are going to focus on this. This extended formation can achieve some benefits for distances between 10 and 40 wingspans. As you can guess, these benefits are going to be lower than in close formation, especially when we are talking about distances greater than 20 wingspans. So in order to follow like a conservative approach in this work, we are only considering extended formations for distances between 10 and 20 wingspans. I also have talked at the beginning about a second issue, not only the environmental impact, but also we need to increase the capacity of the ATM system. So formation flight can also help to get that because according to the ICAO, the formation is going to be seen as a single aircraft regarding air traffic control purposes. So they also can help to reduce the workload of the controllers. So we are going to focus on this, on the formation flight planning problem. To give you a better understanding, imagine that we have this whole set of transoceanic flights in this case. And the first thing that we need to do, it's the partner allocation. Normally, this optimization problem is going to be disaggregated in a V-level optimization problem. And the higher level, is the partner allocation, in which from all of these huge number of flights, we need to choose smaller subsets containing good candidates for flying information. So we are going to have 2-3 flights that could be good to fly in a formation. We can consider more aircraft, for instance, 5 aircraft to fly in a formation, but in previous research, it's given that it's very difficult to coordinate in a well manner more than 3 aircraft, so we are only consider a maximum of 3 aircraft in the formation. So this first problem is giving us these smaller subsets, and we need to do a second step. For each of these subsets, we are going to solve the formation mission design problem. Here we are going to use optimal control techniques in order to study if for each of these subsets containing the 3 flights, for instance, if the optimal solution is for them to fly in a third formation, in a third aircraft formation like this, or maybe the optimal solution could give us 2 of them flying in formation and 1 of them flying solo, or maybe the formation is not optimal and we are obtaining 3 solo flights. We are going to focus in this formation mission design problem. There are a lot of studies that have demonstrated the science, theoretical and experimental studies. They have demonstrated the potential of formation flight, and currently we can focus on this fellow flight project that it's carried out by Airbus, which is working together with air navigation providers, airlines, controllers, and also aviation organizations in order to establish the standards and the procedures for commercial formation flight. We are going to focus on this formation mission design problem, and in particular, we are going to include uncertainties to the problem. Because there are a lot of studies, the potential of formation flight has been demonstrated, but there are no previous studies about stochastic formation flight. And we think that this was very important in order to ensure the operational feasibility of commercial formation flight. So our problem is given as follows. We are going to have the information of 2, 3 flights with its, for instance, arrival and departure times and locations. We also are going to have the meteorological data, and we are going to assume to know the expected fuel savings, the expected benefits from the formation. So we are going to have different parameters or variables that are going to be uncertain, and we need to solve the problem and establishing if the formation flight is optimal or not. Our algorithm is going to decide it. And also, it's going to give us the stochastic trajectories, the stochastic optimal trajectories. And of course, in case of formation, we are going to have the rendezvous point and the splitting point of the formation. The locations and also the times. This is needed in order to a planning phase for the flight plan, for instance. So let's go to the model. We are going to use typical ATM assumptions, so I'm not going to be quite deeper on them, but only one thing that we are going to consider, that formation flight is only possible at the cruise phase. So this is going to simplify a little bit our dynamical model. We are going to have this model in which we have 5 state variables, both geographical coordinates, latitude, longitude, heading angle, the velocity, and also the mass. And we have 3 controls, but with this algebraic equation, 2 of them are related to each other. So in fact, we are only having 2 degrees of freedom. We also are going to have some flight envelope, a typical one. Okay. All of these, the parameters of the model and also of the flight envelope are given by the Eurocontrols database, BADA, in its version 4.2. And here it's one of the particularities of the formation flight, because here I'm talking about a general dynamical system for any aircraft, But when we are flying in a formation, if we are the leader, for instance, we are going to have this mass flow rate equation. But if we are the trailing and we are achieving these benefits from formation, we need to change this differential equation. And we are going to have something like this, in which this R field is the benefits achieved by the trailing aircraft in the formation. Given by previous research, this from experimental and also theoretical one, this parameter is between the 6 and the 14%. Of course, it depends on the meteorological conditions, the aircraft that are involved in the formation, but here we have only these numbers. So this is one of the particularities of the formation. Here we are including this wind forecast given by some reanalysis data. And of course, we have also a typical objective functional in which we are considering a simplified direct operating cost, in which we have two terms, the flight time and the fuel consumption. We need to take into account here that a formation is going to reduce the fuel consumption, but also it can increase the flight time, because one or more aircraft involved in the formation may need to change its optimal solo route in order to join the formation. Sorry. So now we are going to focus on the methodology and the formulation of the problem, that it's formulated as a switch stochastic optimal control problem. Here we have the general overview about this, the general formulation about this switch stochastic optimal control problem, in which we are going to have this dynamical model in which F can be F1, F2, F3, as in our case that we have for the mass flow rate equation. We are having different dynamical equations. And also one important thing is that normally for this switch optimal control problem, we are having some binary variables like this one, okay? And also this theta, it's used to the random variables. That's why we have this stochastic optimal control problem. So, starting with this switch optimal control problem, we tried to avoid using binary variables because they are like very bad in computational times. So we are going to avoid them. The problem here is that this is a bit tricky information flight because we have two different dynamics, but the system is not free to choose between them. The trailing aircraft only can choose this dynamical equation if the distance is between 10 and 20 wingspans. So we have these two different dynamical equations related by a logical constraint. And this logical constraint is a disjunctive constraint. This and or our distance is greater than 20 wingspans, or our distance is lower than this 20 wingspans. So we need to match these two things, these logical constraints and the different dynamical equations, and we can reformulate the mass flow rate equation like this way. But in here, these variables are still binary. So using the embedded method, So using the embedded method, we can transform these binary variables into continuous one in order to avoid these difficulties to the computational problem. Okay. Then this is like the switch part of the switch of stochastic optimal control problem. And now going to the stochastic, of course, as we have said, we are including some uncertainties in the problem. This is quite recommended in order to improve the realistic solutions that we are getting. And in the formation flight problem, we are going to have typical uncertainties that we can also find in a solo flight, like for instance, uncertain in the initial weight of the aircraft, or uncertainty in weather data, in meteorological data, but also we can find some uncertainties inherent to formation flight, as is the fuel savings due to the formation. So with these uncertainties, including them in the optimal control problem, we are having this stochastic optimal control problem. In this work, we are considering uncertainties in the departure times of the aircraft, of all the aircraft involved in the formation, and also in the fuel burn savings. And one assumption is that we know a priori the PDF, the probability distribution function of these uncertainties. Knowing these PDFs, we can use the generalized polynomial cause expansion to solve it. I'm not going through this quite deeper, but this method, this expansion, gives us the possibility to approximate the stochastic optimal solution with a finite sum in which we have some deterministic coefficients given by the expansion, and also the multivariate orthonormal polynomials. And thanks to this, once we have calculated these coefficients, we also can compute some statistical information, such as the expected value or the standard deviation or the variance of our stochastic variables in these terms. So including all of this in the optimal control problem is going to give us the chance to convert this original stochastic optimal control problem, that it's quite ambitious to solve it, into a deterministic one. Of course, now our deterministic problem is going to be an augmented deterministic problem in which we are going to have a lot of variables, but the equations are quite smooth. So we can use we can use classical optimal control problems methodologies to solve it. In this case, we have used the pseudospectral noting method, but any Hermite-Simpson or maybe the trapezium could be used to solve it. So I'm going to present two results. The first one, we are considering a formation of 3 aircraft, and we have uncertainties in the fuel burns, in the fuel benefits due to the formation, and a second one in which we have only 2 aircraft, but the uncertainty is in the departure times of both aircraft. These are the characteristics that both experiments have in common. In both of them, we are considering transoceanic eastbound flights from North America to Europe. We are considering in all of them Airbus 330-200. We are going to establish, to set some initial and final values for the variables, and the arrival times are free. So for the first experiment, we have here the scenario. We have these 3 flights with the different departure times given here. Like, for instance, flight 1, the green one, goes from New York to Paris, departing at 10:15. And our Our random variable here, it's the, as we have said, is the field burn savings due to the formation, and is given as a Gaussian distribution in which we are considering a 10% of expected value of the PDF and a standard deviation of 0.02. As you can see here, this is a non-optimistic scenario because the distance between the arrivals, for instance, is greater than 1,000 kilometers. So maybe it's not the best, the most optimistic scenario, but we want to see if we could achieve some benefits from the formation in this non-optimistic scenario. And indeed, we have that the formation flight is optimal. Here we can see the expected values of the trajectories. And here we have included these expected values together with the 95% of the confidence envelopes regarding the uncertainties in these field savings. We can see, for instance, that flight 2, the blue one, is the one with the greatest spatial variability. Here we have information about the sum of the state variables. For instance, here we have the evolution of the mass. If we go to the blue line, we can see that there is no variability. And this is why, this is because aircraft 2 is going to fly as the leader one. So its mass evolution is not going to be affected by the field savings due to the formation. However, if we go to aircraft 1 and aircraft 3, we are having these benefits from formation, so we have some variability on the mass. Also here, the heading angle, that once again, we have the greatest variability for flight 2, for aircraft 2, and here the Mach, that we can see that we have a great variability, especially on the first period of flight 2. Here we have the control variables that are quite smooth. And here we have the numbers about the objective functional. As expected, we are having that the flight time variability is very low. It's not quite much affected by this uncertainty in the fuel savings. However, the fuel burn for the different aircraft is affected by this variability, because they are going to affect the whole formation flight, and especially this mass flow rate equation. In terms of the total reduction given by the formation flight, we can talk about a reduction of about 2%. That maybe you can think that it's not so much, but this is only achieved by changing the way of flight with no any other thing. And remember that we are considering a non-optimistic scenario. This 2% of total emission, because, for instance, we have said that flight 2 is the leader, so it's increasing its operating cost. However, flight 1 and flight 3 are reducing them. Okay, here we are talking about the total related to considering the three aircraft. So maybe this 2% can be significant. For experiment B, we have only two flights that matches with the ones for the former experiment, and here our uncertainty is in the departure times. To have this the PDF of these departure times, we have used a Gaussian mixture distribution. We have obtained real data from JFK and the Boston airports, and we have approximated this data with this Gaussian mixture. So here are the PDFs that we have used to include these uncertain parameters in the problem. Once again, we have that formation flight is optimal in the solution, and now we can see that the variability for both flights are very big for both the latitude and the longitude coordinates. Also here we can see that now what we are seeing here is that the variability is high, so it means that having uncertainty in the departure times is given to our solutions a lot of variability. Our solutions depend quite a lot on these initial departure times. Here are the control variables that are once again quite smooth. And here we have the numbers. Now, if we go to the standard deviation for both the flight time and the field bound, now we can see that the variability is high. So this uncertainty in the field savings affect both of the terms of our objective function. And of course, now we are achieving only a 0.1 of reduction of the total direct operating cost. That this gives us an idea that if this is going to be implemented in real scenarios, we need to include some mitigation measures. Like, for instance, if one of the aircraft is delayed, you are not joining the formation. You need to change the candidates for the formation. Now I'm going to present in which I'm working now, because this was like a first study in order to see if taking into account these uncertainties in the formation mission design problem could give us some benefits or not. And once this has been assessed, now we want to go a bit deeper and establish some standards, some procedures related to this commercial formation flight. Because as you can imagine, for solo flights, we have everything well established, but for formation flight, it's nothing fixed. So for instance, now we are focused on the field policy related to this commercial formation flight. And we want to answer questions like, should the aircraft that are going to be involved in the formation carry the same fuel that if they are going to fly in a solo flight? Because if you are going to have some savings in your fuel consumption, maybe you can carry a bit less or not. Because what is going to happen if you think that you are going to join to a formation, but finally something happens and you can't join to the formation? So all of these are the things that we are trying to look for an answer for them. And to do this, we have seen that we need to go deeper to the formulation of the problem. And now we were using, in the former scenarios, we were using algebraic constraints given by this, like the mean of the final mass should be greater than the reserve fuel and the quantity of fuel that you want to have, some minimum value. But this is not enough, and we need to include some probabilistic constraints that are called chance constraint, like this one. Now, what we are including in the problem is if the probability of having a final mass greater than some minimum value, it's greater than 99%. So if we can ensure with a probability of 0.99 that our final mass is going to be greater than our minimum value. And this is needed in order to establish some procedures related to risk analysis and operational feasibility. Following a spectral approach similar to the one explained for the GPC, we can convert these probabilistic constraints into some algebraic constraints like this one that can be incorporated to our switch stochastic optimal control problem in an easy way. So here we have some of the preliminary results that we are achieving. For instance, here are zoom in to the final steps of the evolution of the mass, having what I have called deterministic constraints, because here we have only the mean of the final mass. And if we this is just a zoom about this last part. And if we go to this green figure, we can see that, okay, the mean is not going through that minimum value, but all of this is variability of the problem. So if you are flying in any case in which it's considered here, you are not arriving to the final point with the needed fuel established in your policy. However, when we include these probabilistic constraints, now our variability at the final points it's quite lower, and we can ensure with a probability of 0.99 that we are fulfilling this inequality. Of course, including these probabilistic constraints are also affecting the operating cost of our problem. If you are including more constraints, your objective functional is going to be worse. As in this case, we can see that it's affected by almost 2% for the fuel consumption and 1.3% for the flight time. Finally, just to conclude, we can say that formation flight could be beneficial, and we can give it an opportunity, continue with studies and some research. This proposed methodology is quite faster than previous ones, so this gives us the opportunity to include it to be used by flight dispatchers and include it in the different phases of the flight plan. In spite of including these uncertainties, we are having computational times of the order of 4 or 5 seconds. So we can use it. And yeah, as most of you are thinking, this is not yet a reality, and maybe we won't see it. But the truth is that we are having the different stakeholders collaborating to make it possible in the near future. So thank you so much.